Warning: the video you're about to watch contains mathematics at the level of pre-calculus. All material has an assumed prerequisite of college algebra and trigonometry. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Casitas River College in Sacramento, California. This is a continuation of applications or models of exponential and logarithmic functions. It is assumed that you've watched all my videos on exponentials and logarithms up to this point. If you have not, I recommend you going back and doing that because I'm not really going to cover any type of review here. So this one's focused on Newton's law of cooling, this video that is. The following theorem is not memorizable, but it does get used in calculus. And at that time, again, you get reintroduced to it and you actually derive it. So, Newton's law of cooling, really cool, pun intended, I guess, but it's a really, really cool theorem. If you have some object, could be coffee, it doesn't really matter. Actually, coffee kind of aligns with my last example. I did a Starbucks example last. So let's say you have a Starbucks coffee and its initial temperature is D naught. This guy right here. That's the difference. So let's say the difference between the ambient temperature, which is, the surrounding temperature around us. So let's say it's 75 degrees outside. If the difference between the hot coffee's temperature and the ambient temperature is D naught, there we go. And if its surroundings have a temperature of T sub S, which would be our 75 degrees in the example I'm stating, then the temperature of that coffee or of that object at any given time is modeled by the function. Temperature at time T is equal to the temperature of the surrounding area plus the difference between the temperature of the surrounding area and the temperature of the object in question, times e to the negative kt. And here's the thing about that negative kt, or at least the k. The k is positive, so negative k would be negative, and it depends on the type of object you're working with. So if it's metal, then k is more, since metal's more conductive, it might lose temperature much faster. Okay, and if it's, I don't know, some other object, cardboard or butter or whatever, k will change depending upon the actual substance you're working with. So if it's coffee, the k will be different for coffee than it would be for metal or for flesh or whatever it may be. So again, that formula is not memorizable, but let's see how it works. Suppose that the coffee from the last example, there we go, was originally 185 degrees. That's our initial temperature of the coffee, not the surrounding temperature or the difference. It's just the initial temperature of the coffee. And the woman who purchased it took it outside and set it on the table for some weird reason in the 40-degree winter air. There we go. So we know the temperature of the surroundings, T sub S, is 40 degrees. After 10 minutes, the coffee was only 125 degrees. And by the way, I used to do this example in class. I had a little thermometer that I'd hook up to a calculator, and then I'd bring in hot water actually, and I'd put that thermometer in there, and I would just lecture, and you could see the temperature go down as data points throughout the lecture, and then we'd figure out what the constant was for the temperature decay. And it really does follow Newton's law of cooling. It perfectly follows it, in fact. So anyway, after 10 minutes, the coffee was only 125 degrees. Find the function that models the temperature of the coffee at time t. Well, we have enough room on this page to work, so I'm going to go ahead and use this full page for this problem. We know that the temperature at any given time is modeled or given by this formula, T sub S plus D sub 0 e to the negative kt. We also know that the temperature of the surroundings is 40 degrees. So T sub S equals 40. We also know that the difference between the surrounding temperature and the temperature of the coffee can be modeled or can be found just by taking the difference between 185 and 40. So we're going to go ahead and do that. It's important to note D naught is the initial temperature difference between an object and its surroundings. So it'll be the temperature of the object minus the temperature of the surroundings. That's how this works. So let's go ahead and look at the temperature of the object, 185 degrees. And we're going to subtract off the temperature of the surrounding air, 40. And so the initial difference is just 145 degrees. The reason why I need to make that clear, that is the temperature of the object minus the temperature of the surroundings, is because this value could be negative if you put a cold item in a hot room. The cold item, let's just say it's ice, and it's at 30 degrees initially, and you put it in a room that is at 90 degrees. Well, then D naught would be negative 60. So it's very important to note that difference is the temperature of the object minus the temperature of the surroundings. It's very important to note that. Well, that being said, we have almost everything we need. Let me just go ahead and plug this stuff in. This is going to be 40 plus 145 e to the negative kt. If you need to know that this works, you could let t equal 0. If you let t equal 0, you'll get e to the 0th here, and e to the 0th is 1. And you find that at time 0, you have 40 plus 145, or 185 degree coffee, which is true. I'll plug it back in, that negative kt. But I'd like to know what k is. To find k, you need a piece of information. And luckily, they tell us that after 10 minutes, I'll just highlight that here. After 10 minutes, the temperature was 125 degrees. So that one single piece of information will identify K for us. So it'll tell us the decay or temperature coefficient for this coffee. It's actually a heat transfer coefficient, but whatever. So let's go ahead and do that. So I know that if I substitute 10, was that what it was? Was it 10? Yeah, 10 for time. So 40 plus 145 e to the negative k times 10. I know that the temperature, the output, will be 125. Again, I'm going to just double check that. Perfect. Now, I just need to solve for k. Subtract 40 from both sides. So you get, what is that, 85 is equal to 145. E to the negative 10k. And then divide both sides by 145. And you get 85 over 145 is equal to e to the negative 10k. And you can see very nicely a natural log of both sides will be beautiful here. So just take the natural log of both sides, or if you want, log base 10. Doesn't actually matter. 145. And you should know, if you take the natural log of both sides, natural log of e to a power is just the power. That's why natural log is a good choice here. And then divide both sides by a negative 10. Divide by a negative 10. So natural log of 85 over 145, and then divide that by negative 10. That will be our value for k. Now, you probably want to keep that as exact as possible. So if you have a calculator that can save values, I highly recommend it. Lucky for me, I go ahead and use Desmos's scientific calculator, or the scientific calculator in Desmos. That's probably a better way of saying that. It sounds better that way. So this is going to be the natural log of 85 over 145, and then I'm going to divide that natural log by a negative 10. And I get that k is approximately, and I'm going to carry out to 4 decimal places here, 0.0534. So I'll just say this is roughly 0.0534. Again, I'm going to use Desmos. That number I've saved as k in Desmos. So when I do any computations with this, I will actually use the k that I've saved in Desmos. So let's see, did we answer part A? Find a function. Yep, we sure did. The function is going to be this function right here. In fact, I should probably write it just right here. So it is t of t is equal to 40 plus 145 e to the negative kt. And I'll just say where k is approximately, not exactly, but approximately 0.0534. Again, when I go to use this formula, I'm going to use the exact value of k, not the approximated one. Well, part B is just how long, basically using our formula, how long before the coffee reaches 90 degrees? Well, that just requires us to take the formula we just wrote down and let the output temperature be 90 degrees. I want to know, we need to solve, I should say, 90 is equal to 40 plus 145 e to the negative kt. Again, k is a constant we know, so not a big deal. If you subtract 40 and divide by 145, so notice I'm going a little bit faster, but you should be okay with this. You get that. If I take the natural log of both sides, you get this. Remember that we have k saved, so that's okay. And then divide both sides by a negative k. So t is going to equal natural log of 50 over 145 divided by a negative k. So how long does it take for that coffee that's sitting outside to get down to 90 degrees? Maybe that's the drinkable temperature for this person. So I'm going to go over to Desmos. I'm going to use the k that I have saved here. So the formula for time was that we got was natural log of 50 over 145. Hop outside that, and we're going to divide that by a negative k. So roughly 19 point, and remember the time unit that we have here is minutes. So roughly 19.9 minutes, or if you're willing to round up, 20 minutes. But I'm going to put 19.9 minutes. Approximately 19.9. And again, I will use the units here, minutes, because I need people to know how long it takes. So 19.9 minutes. And then what's the horizontal asymptote of the function? That's kind of odd. It just, all of a sudden, it got mathy. Prior to that, it was kind of a physics question, right? How long does it take to reach 90 degrees? Set up this function, whatever it is. But now it's like, what's the horizontal asymptote? That seems to be a crazy question, but actually it's not too crazy. If you think about our function, which again is this guy right here, plus 145 e to the negative kt. And if you recall that k is positive, then you could use transformations to graph this. You could say, well, that's the same thing as 145 e to the negative kt, where again, k is positive, so that's e to the negative power plus 40. You can kind of use transformations. Now, this is actually, now that I'm thinking about it, this is a great example to showcase why understanding the base graph of a function is critical. Nobody's actually asking me to graph this, but I happen to know if I have an exponential function with a negative exponent, so e to the negative x, or something like that, it's decaying. I don't care how quickly it's decaying, it's just decaying. And it's tending to 0. But if you add 40 to it, then you're actually lifting that graph up by 40 units. So here's the t-axis in this case. And you've lifted this graph up by 40 units. This is y equals 40. This is what's so critical about truly understanding base graphs, is that you don't have to really know what the graph, you do have to know what the graph looks like, but you don't have to actually graph it out if you just know, oh, it's an upside down exponential or a decaying exponential lifted up 40 units. Well, I know what an exponential looks like. A decaying exponential decays to 0, but if you add 40, it decays to 40. And so if I asked, what's the horizontal asymptote? It's 40. Now let's think physically why that's true. So I'm going to answer the question, y equals 40 is the horizontal asymptote. But let's just do a logic check here. Why is it that as I allow that coffee to sit outside in that 40-degree temperature, why would the temperature eventually reach 40 degrees? Well, that's a silly question. You know why it's going to reach 40 degrees, because it's going to reach the temperature of the ambient surroundings. Because everything in a system kind of wants to go to static levels. That's kind of the steady state of this system. So anyhow, very important that you understand. There was a lot of good things in this example, actually, but probably one of the best things is really using our transformations very quickly to understand what the horizontal asymptote is and to be able to describe why the horizontal asymptote is what it is.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.